Hello, welcome to Thermal Horizon Engineering Capstone presentation. Just wanted to give everyone a quick appreciation for their time in viewing this program. A quick introduction of a contributing team, beginning with myself, Curtis Trang, Sandra Egblor, Alexander Huang, Alexander Mitrovic, Mohammed Sakur, and Adnan Shaban. We are also pleased to have had the pleasure in working with their Capstone client, Connor Spear, and Capstone advisor, Dr. Li Xuanzhang. The world's slowly shifting to a zero-carbon net culture, with renewable generating technologies such as solar panels becoming more cost-effective and efficient system. However, we're also seeing supporting infrastructures such as batteries or storage systems to conserve that energy to have either been inefficient or limited in functionality. With the problem, this comes with an opportunity, as we are seeing a projected shift towards renewable technologies such as solar panels and electrical vehicles. There's a business opportunity in having an energy storage system that provides all the amenities for a residential homeowner and providing power, heating or cooling, as well as a source of fuel to their electrical vehicles. This is essentially a one-stop shop for energy to a residential homeowner and has a huge potential as a business consumer product. I'll let Sandra explain more on the objective for this business opportunity available.
Thanks, Curtis. The main objective of this project is to develop a residential pumped heat energy storage system. This involves the design of the thermal reservoirs, heat exchangers, and piping that can store heat energy to later convert to electricity. The system should also be capable of providing heating and cooling to the home. Some of the key specifications of this project are shown in this table. The system must be capable of discharging 15 kilowatt hours of electricity with a continuous output rate of 5 kilowatts and a peak output rate of 7 kilowatts. This design will store heat energy for 24 hours, which means that after this storage period, the system should have enough energy to be able to produce the 15 kilowatt hours of electricity. The round-trip efficiency should be in the range of 70 to 80%. Round-trip efficiency is defined as the energy that is retained by the system after the 24-hour storage period, divided by the energy into the thermal reservoirs. Lastly, the system lifetime should be 25 years. Now I'll pass it off to Alex, who will discuss the three concepts that we developed during phase 2 of this project.
Thanks, Sandra. So going to phase 2 of our project, Thermal Horizon developed three concepts to explore various approaches to meet our client's specifications. A common solution was to use phase change materials, PCMs, for the thermal energy density at their melting points. Thermochemical heat storage was also considered for its exceptionally high thermal energy density, but it was disregarded for its high cost and diminishing performances through charge cycles. Our first concept, reverse charging, utilizes sensible heat storage, with approximate dimensions being 4.9 meters by 4 meters by 1.7 meters. The system uses water for the hot reservoir, heated from 58 to 80 degrees Celsius, and uses Dowtherm J for the cold reservoir, cooled from 21 degrees to negative 60 degrees Celsius. This system is capable of providing heating and cooling to a home as well. For the system, 2 reservoirs are used per loop, and the medium is moved between 2 reservoirs to exchange heat with the heat engine. The initial cost estimate for Concept 1 was $28,571. Downsides to Concept 1 are that sensible heating does not maintain a constant temperature. Hence, the performance of the heat engine would be inconsistent. And out of the 3 concepts, Concept 1 is also the most expensive and has the largest footprint. Concept 2, ambient cooling, utilizes latent heat storage for its hot loop and ambient outside air for its cold loop, with approximate dimensions being 1.3 meters by 1.1 meters by 0.8 meters. This concept is able to maintain a somewhat constant operating temperature by using a combination of latent heat and outdoor ambient air as a cold reservoir, allowing the heat engine to provide a consistent output. However, one large downside of the system is that it is very susceptible to dramatic changes in outdoor temperatures, such as changes in seasons, which would significantly fluctuate the cold reservoir's temperatures. Hence, the system's performance in the winter would be dramatically different to that in the summer. Since this system uses ambient air for its cold reservoir, it is unable to provide cooling to a home, but it is able to provide heating since it has the physical hot reservoir. Since Concept 2 has no physical cold reservoir, it's able to have the smallest footprint out of the 3 concepts, as well as the lowest cost, which was initially estimated to be $7,320. Concept 3, two phase change material reservoirs, uses latent heat storage for both loops, with approximate dimensions being 3.5 meters by 3 meters by 1.1 meters. For the hot loop, a barium hydroxide salt hydrate is used at its melting point of 78 degrees. For the cold loop, a phase change material called SP7 gel by the company Rubitherm is used at its melting point of 6.5 degrees Celsius. Heat is transferred between the reservoirs and the engine by water as the working fluid. This concept is capable of maintaining constant operating temperatures regardless of season, allowing the heat engine to provide consistent power to a home. Since this concept has two reservoirs, it is capable of providing heating and cooling to a home as well. Concept 3 has an initial cost estimate of $16,038, and between the three concepts, Concept 3 has the most intermediate cost and footprint. Moving forward, Thermal Horizon Engineering has ultimately decided in developing the third concept further. Factors that contribute to this decision are that Concept 3 is capable of providing heating and cooling to a home and operates within the most reasonable operating temperature range, from 6.5 degrees to 78 degrees, whereas Concept 2 operates at a maximum of 222 degrees, and Concept 1 operates at a minimum of negative 60 degrees. Since Concept 3 also uses two phase change materials, we can expect the most consistent performance from the system. Lastly, although the system is not the cheapest nor the smallest, the other contributing factors were determined more important. Going to phase 3, Thermal Horizon has also made some changes to Concept 3, such as changing the initially selected PCMs to PCMs provided by the company Plus Ice. The hot medium temperature was changed to 119 degrees, and the cold was changed to 3 degrees Celsius. This here is a conceptual render of our system, which was designed to be as compact as possible while factoring in insulation. And our system is 2.7 meters wide, 4.4 meters long, and 3.5 meters tall. And now I'll let Alex M. talk about our engineering analysis process.
Thanks, Alex. I'll start with the process underwent for engineering analysis. With the idea of phase change materials as our final selection for energy storage, we underwent a very iterative process to determine the best material. Next, we selected a fitting working fluid that operates at the temperatures we need. Then, with the desired output rate of 5 kilowatts and 7 kilowatts, we use this to determine our mass flow rates. With these mass flow rates, a liquid piping system was designed. With all this, the rate of heat transfer to the storage tanks were determined and a final heat exchanger was designed. With this and determining the amount of phase change material required in each tank, the tank volumes were finalized. With a final design completed, the last calculations performed were the energy losses and the round trip efficiency and performance. These values were used to optimize their tank volumes. Our very first design approach was to select a great phase change material with the following properties. It requires a high enthalpy of fusion, a good density, good thermal conductivity, a reasonable melting temperature for a residential system operation, and it needs to be stable over many repeated cycles. After looking at many different phase change materials from silicone to water to metallics, we settled on three major choices: organics such as paraffin wax, salt hydrates, and molten salts. As you can see in this table, although all three are good contenders, salt hydrates and molten salts missed out on one key spec. Salt hydrates were not desired as they are very unstable after many cycles, and molten salts operated at temperatures too dangerous for a household. Therefore, our final selection is the organic phase change material. Compared to the other two, it also provides the benefit of being non-corrosive to metals. This table shows our final selection of phase change material. We're using Plus Ice's organic material product A2 and A118, which melts at 2 degrees and 118 degrees respectively. With the phase change material selected, it is now on to working fluids. When it came down to working fluids, we initially used water as a working fluid as it is easy to use, non-toxic, and inexpensive. But as the design's Carnot efficiency greatly needed an improvement, we needed to change the temperatures of our system. With this, the two melting temperatures of the phase change material needed to be outside of water's operating range. If we continued to use water, there would be a significant risk in the water either freezing or boiling. So the solution to our problem is Dow-Therm J and G, which is a heat transfer fluid provided by the Dow Chemical Company. These two heat transfer fluids would avoid any issues of freezing and boiling while also avoiding any possible ignition problems as they would operate under their flash points. Finally, Dow-Therm J would be used for the cold loop and Dow-Therm G would be used for the hot loop. Now, On to Mo to explain the mass flow rate calculations.
Thanks, Alex. To determine the mass flow rates of the working fluids in our system, the PCM temperatures were first considered. Using these temperatures, we determined the Carnot efficiency and the coefficient of performance, and then used these performance measures to relate the rate of heat transfers for charging and discharging of both the hot and cold loops. By then also relating these values to the work in and out of our system, we were able to solve for the mass flow rates for each working fluid. This was done for charging at 5 kilowatts, discharging at 5 kilowatts, and discharging at 7 kilowatts. For the liquid piping design, we followed 3 main stages: material selection, calculations, and pipe and pump sizing. For the material selection, Schedule 40 was used for the exterior piping, as it has low conductivity and minimizes the amount of heat loss during storage. For the heat exchanger, copper was used as it has a high conductivity and therefore facilitates heat transfer. For valves, we used a combination around all the different equipment in our system to make sure that we can isolate it and maintain it as required. Also, 3-way valves were used on both the hot and cold loops to help divert heat and cooling to the residential home. Also, these 3-way valves help with interacting with different renewable energy sources, such as solar heating, to add heat into our system and increase the efficiency. For calculations, we started with the pressure drop. This was done for the hot and cold loop, and we used Bernoulli's principles for those calculations. Also, minimum pipe and tank thicknesses were calculated to ensure that they comply with the required or the relevant codes and standards. Finally, NPHSA calculations were done to ensure no cavitation during the pump selection phase. For sizing, 2.5-inch pipes were selected, and this was done by using the 3-foot water gauge per 100 feet industry standard, as well as the mass flow rates we already calculated. For pump sizing, we used the mass flow rates as well as a total pressure drop in the system to select relevant pumps. 2 1-horsepower pumps were selected. For the heat exchanger analysis, the objective was to determine the required surface area of copper required in each tank to satisfy the required heat transfer. So this was done to accomplish a 1 degree difference of the working fluids at all outlets from the PCM temperatures. So to start this, we related all the heat transfer rates to the overall heat transfer coefficient, surface area, and logarithmic mean temperature. As a result, we were able to solve for 4 different surface areas, 2 for each tank, 1 for charging and 1 for discharging. In order to satisfy all the different operations and processes our system goes under, we selected the highest surface areas we determined. For tank sizing, we first had to consider the fact that our system needs to store energy for a total of 24 hours. As larger tanks result in more heat loss, we had to go through an iterative approach in order to get a converged value of 15 kilowatt hours after storing energy for a whole day. The final tank volumes were 1.4 meters cubed for the hot tank and 2.4 meters cubed for the cold tank. In the tank and heat exchanger, for the tanks, we decided to go with cylindrical tanks, as cylinders have a high volume to surface area ratio and are much easier to manufacture compared to other shapes such as spheres. For the heat exchanger, we decided to use a coil copper design for high compactness. Also, both tanks were insulated with 6-inch mineral wool material. And this 6 inches was determined by plotting the relationship between the heat lost and the insulation thickness. After 6 inches, we realized that the majority of the heat lost is reduced. However, we didn't want to continue adding thickness, as this would make our system very, very large. So we had to consider both compactness and efficiency here. Also, caps were installed on both tanks at the top to facilitate the installation of the PCM materials. When it comes to efficiency, we defined our round-trip efficiency to be the total work out of our thermal reservoirs over the total work into our reservoirs. So here we neglected the inefficiencies of the heat engine and heat pump, as this part was out of our scope. The maximum efficiency our system could reach was 73% in the case that the system discharges as soon as it fully charges. However, if the system was to store energy for a total of 24 hours, we would only get an efficiency of 68%. The majority of losses here are due to the pumping work required to circulate the working fluids that are in the system, followed by the heat loss through the hot tank during storage. In terms of system cycles, a fully charged system requires 29 hours of charging. However, the system can start to provide heat to the home after just 14 hours. Furthermore, the total discharge time for the system is 3 hours. The system always produces 15 kilowatts of electricity. However, a total of 129 to 134 kilowatt hours of heat can be provided depending on the discharge time of the system. Also, up to 7 kilowatts of cooling can be provided if the system was to discharge right after charging. Thank you, and now I'm going to pass it on to Adnan.
Thanks for the introduction. The design we're offering has a number of successes and limitations that describe its feasibility. Successes are seen where we met or exceeded specifications, while limitations are where we failed to meet specifications. These failures do not cripple the system in any way, just limit its feasibility and use case. The system itself is very easy to maintain over its lifetime, since materials are non-corrosive and non-toxic. The working fluids are also known to not congeal or break down over time, as they were tested to over 10,000 cycles. Therefore, our maintenance would focus on replacing parts for the pumps or the pumps in entirety. In terms of electricity, heating, and cooling needs, this system does its job, and when completely charged, can continue to supply heating and cooling needs while remaining fully charged. It should be noted that the working fluids are mild skin irritants, but they pose no serious health risks. Despite the advantages I just mentioned, the system does come with some serious limitations. The system weight is upwards of 5,000 kilograms and the cost upwards of $100,000, which is significantly more than competing products. Due to the weight of the system, the installation process would be quite complex and people would have to be well trained. These problems, though, are almost entirely due to assumptions that have decreased the system's overall efficiency and as a result increased the volume of PCM needed. This increase in volume also drove up the size of all other components in the system, which in turn drove up the cost. The largest costs and weights are shown in the table and are attributed to the working fluids, phase change material, and heat exchangers. Future work focuses on how to reduce the limitations on feasibility, as well as a plan for future research based on this design. The first step here is to work on the development of a suitable heat pump for this system, with the focus on maximizing efficiency. Improving the real efficiency will help reduce the size, weight, and cost of the system, since less heat would need to be stored to meet electricity specifications. The next area of study is working fluids and PCMs. They were thoroughly researched, but there is definitely more work that could still be done to determine a cost-effective solution that still meets our specifications. The final area of study would be the development and testing of a prototype system. This would allow us to test our assumptions as well as performance predictions. This information would help us further optimize the system and give us a more accurate representation of the actual system cost. Now, I'll pass it on to Alex M. to wrap up this presentation. Thanks.
Thanks, Adnan. To give a final conclusion, the final design satisfied the key requirements set out initially for the project. The system satisfies the required power outputs, provides heating and cooling to the home, and maintains this for a 25-year lifetime at an effective efficiency range of 68 to 73%. With its adaptive connections, it is also compatible with the renewable energy sources such as solar and wind power. Looking towards the future, it is desired for the system to be used in helping the lagging development of the supporting infrastructure in the renewable technology sector. This is also an opportunity to provide users with a green solution to their electrical heating and cooling needs. I'd like to thank Dr. Zhang, Dr. Nakashima, Dr. Nobes, and our client Connor Spear for all the help they provided us throughout the design of our system. Thank you for your time. Thermal Horizon representatives are available from 6 to 8 p.m. on April 8th for any questions or concerns. Thank you.